Hello, today what we're going to do is figure out how to graph absolute value functions and also identify all sorts of information about them from the equation or from the graph. So I start with this one example, and we should be able to build all the knowledge that we need for absolute value from this one example. Now if you look at the equation, it reads sketch the graph of y equals negative absolute value 2x plus 5 and then minus 3, and we have to identify everything about it. Well, the first thing that you may want to notice is that we have this absolute value thing going on in the graph, and that should make you wonder, hey, what will that graph actually look like? So what we want to do is figure out what the graph of any absolute value function looks like. And to do that, we can start with the most basic of absolute value functions, which is y equals the absolute value of x. And the way we graph, we remember, is from a table of values. So we make a table of values, and we pick two negative values, 0, and two positive values, and we plug them into the equation to see what we would get back for y. So instead of the absolute value of x, we would have the absolute value of negative 2, the absolute value of negative 1, the absolute value of 0, the absolute value of 1, the absolute value of 2, and we find out what we get back for y. So the absolute value of negative 2 is positive 2, and we have our outputs just like this. Now when we were graphing linear functions, we were able to pick up on a pattern in the x's and y's, but because we're dealing with absolute value, we can't really just say, hey, you know what, if I'm going down by 1, I'm going to keep going down by 1. As you can see with absolute value, some things are going to work a little bit differently. And so we have different outputs. And so the same thing would go with graphing. We want to graph these ordered pairs and see what kind of shape we would get. All right, so we start with negative 2, 2. So we have a point on the graph that's up here. Negative 1, 1, 0, 0. And again, we can stop here and think, well, it looks like it's going to be a straight line all the way through. That's not exactly the case. We have to continue graphing because absolute value makes some interesting pictures. So we keep going with our ordered pairs. Positive 1, positive 1, positive 2, positive 2. And it will keep going in that direction. And so since it keeps going in that direction, we can then build our graph. So we can see that the graph of an absolute value function looks kind of like a V. And then we look at our original equation again. We say, well, there's the absolute value bars, but what's the deal with that negative on the outside? Well, that negative on the outside might make something a little bit different. So let's take a look at what we did to graph this and figure out, what might happen if I wanted to graph something with the negative out there. What if I wanted to graph y equals negative absolute value of x? So we'll do the same thing for graphing. We make our table of values, and then we plug in the table of values to the original equation. So we have absolute value of negative absolute value of negative 2, negative absolute value of negative 1, negative absolute value of 1, and negative absolute value of 2. And you see what will happen, because the negative is always on the outside, all of the y values are going to be negative as well. It's going to keep everything negative. So when you look at just this one example, you have the absolute value of negative absolute value of negative 2. Absolute value of negative 2 is 2, but then that negative's there, keeping everything negative. So that's the power of that negative on the outside. And we have our outputs. So now we're going to graph our ordered pairs and see what we may get. What will this graph end up looking like? So we have our ordered pairs. This time it's negative 2, negative 2. So negative 2, negative 2. Negative 1, negative 1. 0, 0. If we're stopping at linear functions, it would go this way forever, but we can't do that here because of absolute value. You may notice I made a mistake on my table of values. I'm going to go fix it there. Good catch for those of you that picked up on it. For those of you that didn't, shame on you. And now we continue graphing. Well, if we have 1, negative 1. If we have 2, negative 2. And now we see what the graph will look like. It's kind of like a V. it's upside down. Okay, so we know for absolute value graphs, if the absolute value is positive, it's going to open up. If the absolute value is negative, it's going to open down. And so we look back at our original equation, and we can tell, hey, because that negative is out there, this graph will open down. Okay, so it's going to be opening down. Well, what about the rest of those numbers? What's the deal with all of those? And for that, what we have to do is learn about the equation form for absolute value graphs. Just like we had with straight lines, just like for the graph with straight lines, we had slope-intercept form, and we had point-slope form, and we had standard form. Well, for absolute value graphs, we have a form as well, and we call it vertex form. And vertex form is a particular form, just like y equals mx plus b tells us all about a straight line. This will tell us all about an absolute value graph. Now this is kind of funky, so we have to get used to, well, what's going to happen. Okay, so just like with y equals mx plus b, the y stayed the same, the x stayed the same, the other letters, the m and the b, told us about the rest of the graph. The same thing is going to happen here. The y stays the same, the x stays the same, the a, the h, and the k are all going to tell us about this absolute value graph. So we got to figure out what that means. And we'll start with a. Now if you remember from the two graphs we had, here was the first graph we played around with, y equals the absolute value of x. What was the a out here? Positive 1, and look what happened. The graph opened up. And if you look at the second graph we had, y equals the negative absolute value of x, the a out in the front would be negative, and the graph opens down. So when you look at vertex form, you can see that what this a will tell you is whether or not the graph opens up or down. Now, what else is interesting about a is it gives us a little bit more information than that. Again, if you go back to our examples, this a here was 1. Take a look at the graph. This graph has something interesting about 1. It has a slope of 1. If you notice on one side, we go up 1, right 1, up 1, right 1. That's the slope. And if you look at the other example, this has a slope of negative 1, down 1, right 1, down 1, right 1, down 1, right 1. So there's also a slope factor that comes in with a as well. So a not only tells us if the graph opens up or down, it also tells us the slope of one of the sides of the v. So if we know that about a, can we then look at our equation from the problem and identify what a is? So you see at this problem, some people might be encouraged to think that a is actually negative 1, which is not really true. If we look at vertex form and we compare that to our equation, we have to notice something interesting that's happening. Inside the absolute value for vertex form, x has a coefficient of 1. If we look at the given equation, inside the absolute value, x has a coefficient of 2. So something tricky has to occur here. And in order to figure that out, we need to go back to some basics from Algebra 1. So when we go back to basics from Algebra 1, we have to remember a little thing called factoring. And if you remember from Algebra 1, if we had an expression, let's say an example, excuse me, that looked like 3x plus 12, we could factor that expression, because these two terms have a greatest common factor of 3. And what we could do is factor the 3 out, end up dividing each of the terms by 3, and inside leaving us with x plus 4. So if we had a term that had a coefficient that wasn't 1 in front of x, we could actually manipulate it so it looks like it has a coefficient of 1. Well, how would that work with something that doesn't divide evenly? We could use the same principle for something that wouldn't divide evenly. What if we had a term 3x plus 11. Could we rewrite this where we have the x looking like it has a coefficient of 1? Very similar to this, we actually could. We have the 3 in front of the x, so we can take the 3, move it to the outside, and just like we did in this example, divide each thing by 3. On the inside, the 3's would cancel. It would leave us with x. And then what about this mess over here? Well, just leave it as 11 over 3. And we can have something that looks like where the x is by itself. So now we go back to vertex form. And we remember, hey, the x has to have that coefficient of 1 on the inside. And we look at our example. Darn it, there's that 2 there. We have to figure something out. So what will we have to do with that 2 is do a little bit of that factoring manipulation. So can we rewrite our equation so that instead of having the 2 in front of the x, where we could have the x just there, excuse me, in fact we can. We can in fact factor out that 2 just like we have done with those previous examples. And when we factor out that 2, what we'll end up doing is dividing each of these by 2. And that will leave us with, on the inside, x plus 5 over 2. So that is a pretty nifty trick. And so we can compare what we currently have with vertex form. The x has a coefficient of 1, the x has a coefficient of 1. And now what we can do is determine from our equation what a would be. Remember, the initial response was to think a was negative 1. In fact, a is actually negative 2. And what will that tell us about our graph? It will tell us the graph opens down, and when it will tell us that the slope is negative 2. And the slope will determine how wide the graph is, how expanded it is, or how compressed it is. Okay, so the slope will tell us. You'll see that when we start graphing in a second. So at least we know now what a would be and what a tells us. And let's go back to vertex form. So remember, forms of equations tell us all sorts of information. Y stays y, x stays x. Everything else tells us something about the graph. So in vertex form, we can also tell the vertex. That's why we can call it the vertex form. So in vertex form, we can see what the vertex would be. Whatever x is, when we have minus h, that is the x-coordinate of the vertex. Whatever h is the x-coordinate of the vertex. Whatever k is the y-coordinate of the vertex. Now you may be wondering, well, what is a vertex? In case you don't remember, the vertex is that point on that graph, like the corner of any graph. That's the vertex. This point exists on an coordinate plane, and so it has an ordered pair to define it. So the vertex is a point on a plane, and the points are defined by an ordered pair, an x-coordinate and a y-coordinate. Now here's where things get a little bit tricky. If you look at where we left off for writing our original equation in vertex form, things get a little bit tricky. So I want to take a trip down memory lane again, just to make sure that we are clear on some things. If you recall, from point-slope form, some things were happening. If you remember, point-slope form is y minus y1 equal to m times x minus x1. If you remember from there, we would have an ordered pair, let's say, of negative 3, negative 5, and a slope of, let's say, 1/2. How would we write that in point-slope form? Well, we'd have y minus y1. Notice what's going to happen when we have minus negative 5. It would look like this. And then we'd have the slope. And then we would have x minus x1. Minus stays the same. Negative 3 turns into plus 3. So we have to remember we have experienced this trickiness before, but we didn't know. So we look at this equation in point-slope form, and remember the point where it came from, the y-coordinate being -5, the x-coordinate being -3. So it's funny that we could understand what would happen from a formula here, seeing the relationship between the formula, the coordinates, and how they look with the plus or minus. The same thing would occur with vertex form. Notice the form. It says x minus h. Notice the x-coordinate is h. And now look at our example. In our example, we have x plus 5/2, so the vertex gets a little bit tricky. The x-coordinate of the vertex is actually going to be -5/2. In the same way that everything worked in point slope, the same thing happens there. Now what about the y-coordinate? And again, to understand the y-coordinate a little bit better, trip down memory lane. We also remember slope-intercept form. In slope-intercept form, when we had y equals mx plus b, if we had an example of an equation that was y equals -2/3 x minus 4, I would ask you, what is the y-intercept? And you would tell me by looking at this, since it's plus b and the y-intercept is -4, then the y-intercept, of course, would be -4. So we know how to deal with a plus b situation. Well, let's use that in vertex form as well. So if you look at our vertex form of the equation, vertex form tells us when we have plus k, the vertex is k, right? The y-coordinate of the vertex is k. In our example, we have the -3, so the y-coordinate of the vertex is -3. So it gets a little tricky. Some people use a shortcut. H is opposite, k is not. Right? If you want to use that as well, that's fine. Now from here, believe it or not, we have enough information to sketch the graph. We have a vertex. We know it opens down with a slope of -2. Let's sketch the graph. Let's see what we get. We have enough information to sketch this graph. So how would we start by how would we sketch a graph like this if we know a vertex and a slope? Well, the vertex is at -5/2, -3. Well, we can count that. We can count that distance. Well, -5/2 is -2.5, right? So on the x, -2.5, about here, down 3. 1, 2, 3. There is our vertex. Excuse me. So we have our vertex. We know the slope is -2. -2 is the slope, means rise over run, right? I'm going down 2, right 1. So from our vertex, we're going down 2, right 1. Down 2, right 1. And since we know this is a V shape that opens down, and we know this is our vertex, we could finish sketching the graph. Down 2, left 1. It's going to look like an upside down V. So we have the information we need to sketch our graph. We can sketch our graph. So the graph looks like this. All right, so let's look at the original question now. So far we have all of this. We get lost because there's so many things going on. Let's go back to the question. We had to sketch the graph of the following equation. Done. We have to identify the parent function. Haven't gotten there yet. Vertex, check. Axis of symmetry, don't know what that is yet. And then transformations from the parent function, whatever that means. So we're almost there, believe it or not. Once we have our graph, we can tell what the axis of symmetry is. Symmetry is when you can fold things in a certain direction and they would be the same. Okay, so wherever things would be symmetrical. Since this is a V going down, if I folded that graph over the vertex, it would match. That would be my axis of symmetry. So we have our axis of symmetry, and we look at that axis of symmetry, and we can tell it's a vertical line, okay? And we should know that vertical lines have an undefined slope, but more importantly, what is their equation? If you look at a vertical line, all of the x coordinates on that line would be the same. So the equation of a vertical line is x equals some number. So back to understanding vertex form. When you have all of this information about vertex form and you're given the vertex, guess what your axis of symmetry would be? It would be the equation that contains all of the x coordinates from your vertex. And then with our problem, we have our vertex. The axis of symmetry would be x equals all of the x coordinates from the vertex. This is an equation of a vertical line. It is this vertical line. We have now identified our axis of symmetry. So now on to parent functions. Well, parent functions are the functions that every other thing that looks like it is built around. So the parent function is what every other function that looks like it is built around. So we have an absolute value function. Well, what does an absolute value function look like? Looks like a v. So the parent function of all absolute value functions is good old y equals the absolute value of x, or you could even use y equals negative the absolute value of x. Either one is an acceptable parent function, as long as you are able to use all the information we have to define how the parent function changes to what we have graphed. Okay, so we know the parent function of any absolute value graph is y equals the absolute value of x. If we know that as the parent function, what we can do now is identify all of the transformations. We can identify all of the transformations from the parent function to what we have graphed. So when I talk about transformations, we're going to talk about how does this parent function turn into what we have graphed. So we can start with the basics. A parent function opens up, our graph opens down. So transformation would be opening down. The parent function has a slope of positive 1. Our function has a slope of negative 2. The parent function has a vertex at the origin. Our function has a vertex that moved. And we have to define, well, how did that vertex move? So the vertex shifts 5/2 units, 2.5 units to the left. So 5/2 units to the left. And 3 units down. And you can tell all of those transformations from the parent function from looking at the graph. But more importantly, you can also tell all those translations of the parent function without even graphing. How could you do that? How could you tell all of this information from here? So let me rewrite the equation that we used. Let's see how these match up. We have our equation in vertex form. Notice the a. A is negative 2. What does that mean? That means it opens down, has a slope of negative 2. So we see our a corresponds to these two transformations. Notice what's happening with the x. It reads x plus 5/2. And remember that tricky thing with the x. Remember, like h could be opposite. What does the x plus 5/2 mean? That means the vertex is shifting 5/2 units to the left. So even though it has plus 5/2, it's shifting 5/2 units to the left. And then lastly, this minus 3 says it's shifting 3 units down. So we can tell all of this information just by looking at the equation. Now there's a lot of tricky stuff going on with absolute value, but these are so transferable to other things later on in Algebra 2. So remember, we have vertex form. The A tells us if it opens up or down. It tells us the slope. The H and the K give us the vertex. The axis of symmetry is x equals h. And let's talk about transformations. In transformations, the H can tells us how far we are shifting the vertex left and right. And the K tells us how far we are shifting the vertex up and down. So all of that from vertex form with absolute value graphs. And that is all for graphing with absolute value.